All right, last time we started looking at area and arc length in polar coordinates, and we had started with area, and we had gotten part of the way through an example number 2, finding the large loop of r equals 1 plus 2 sine 2 theta. We'd gotten to the point finally where we found our limits of integration, basically, right? You guys guessed a whole bunch, and then we did some algebra and found it a lot faster than guessing. And checked it in our calculators, I believe, as well. Yeah? Sound good? Okay. So we are actually ready to... I left my stylus in here last time, but I just don't see it. We're ready to do the area formula. We had encountered that last time. It's right over here. And it's the area is 1/2 between our limits of integration, which we just found last time, and it's our function value, or our radius, squared. So in our case on this one, then our area equals the integral from negative pi over 12 to 7 pi over 12 of 1 plus 2 sine of 2 theta squared d theta. All right, got to square that out. So what do we get? Thanks. That's a good place to start. 1. What comes next? What are my inner and outer terms adding up to when I square? 4 sine 2 theta. And then? Yeah, hang on, let me shift this over just a little bit. You're right, I did. Thank you. Okay, I think all the pieces are there. All right, so I gave you guys a trig worksheet last time. Was anybody not here and didn't get this from me, this trig identities? In particular, the ones that we were finding useful are the ones, they're called power reducing sometimes. I don't have them written on here that way, but they're the double angle identities on the far left, and if you switch it over to the back, it continues onto the back. There's one on here in particular that says the following, and we'll be using it, that the cosine of 2 theta is equal to 1 minus 2 sine squared of theta. So if we were to change this around a little bit, we would be able to get the sine squared in our function to be an angle measure, or to be a double angle instead of it being a squared angle or squared sine. So in particular, I can change this so that I have 2 sine squared of theta is equal to 1 minus cosine of 2 theta, and divide it by 2. So that's the power reducing for sine squared. So let's change that up a little bit. I still have the 1/2 out here in front. Negative pi over 12 to pi over 12 of 1 plus 4 sine of 2 theta. And then I have plus 4, and it would be 1 minus cosine of what angle? Of 4 theta, because I have to double the angle I already have, which happens to be 2 theta. So 4 theta over 2, and then d theta.
Shouldn't your upper limit be 7 pi over 12?
Yeah, I don't know how that happened.
And on your second integral, the row was 2 and then 12.
Wow, apparently I like 2s today, but not 12s. I did it up here too. Oh, you didn't catch that one. You're doing so well. The first one I actually left it off too. So, okay, I think they're right now. It changes the angle to be double what it was. So if you notice in the formula here, this is theta and it becomes 2 theta. But ours is already 2 theta, so it'll be 4 theta. Yeah.
Why is it over 2?
You mean like in my function? Look up at the top. There's a 2 right here from the identity. So I have to divide by 2. I'm trying to solve for this piece, sine squared of 2 theta. So I'm changing this piece and I divide by my 2. Okay. Yeah, and if you feel free to Google power reducing formulas and they'll have them in that form already. I was just using a worksheet that I'd used before and I didn't have that identified on there. Okay, let's keep going.
We just separate it and then we can find the integrals of all of them.
Yes, that's exactly right, Ethan, you're correct. In fact, I think I'm going to move it to another page too because I'm running out of space.
3 plus 4 sine 2 theta minus 2 cos 4 theta.
I'm sorry, what was that?
3 plus 4 sine 2 theta minus 2 cos 4 theta, I think.
Are you taking like a reduced form? Is
Yep.
that what you've gotten after you've done it? Okay. So you had a theta here, right? And then the antiderivative of sine is negative cosine, so you should have gotten a negative 4 cosine 2 theta and then divided by 2. Does that sound right here? I've got looks in people's faces like I didn't do it right. Yeah? Is that good? Okay. It's u substitution that's going on. It's just behind the scenes. So here's a theta. So I'll actually write it out for this one. If you take a look at this piece and you let u equal to 4 theta, in the end when I do the du, I would have to have a 4 that I'm dividing by. So as I do the part that I've sort of highlighted in red, I reduced this, by the way, so that's not even there anymore. But the antiderivative of cosine, of course, is sine, so the sign will stay the same. It's negative sine. It's still 4 theta, but because there's a u substitution there, albeit not a very exciting u substitution, I have a division by 4 from here. Do you guys see that? If you need to see it written out in more detail, please do. Just do the u substitution flat out. So I should have sine of 4 theta. Oh, you guys, and you simplified that part. I haven't done that part yet. That's fine. I think when you guys were giving me the 2, you were combining the 2 from here. Does that sound right? Okay, yeah, I'll do that next. And then I don't need a plus c because I'm going to be evaluating here in a moment. 7 pi over 12 and negative pi over 12. All right, so my 1/2. So there's a theta up here, and there's a 2 theta right here, so that's 3 theta. That's what Ethan had told me earlier. This 4 and this 2 are going to reduce, so I have minus 2 cosine 2 theta, and then plus, and then this 2 and this 4 can simplify.
Over 2.
Sine of 4 theta over 2.
Should that be minus though?
Yes. Okay. And then I have 1/2 in front. The evaluation at the end is the same. I haven't done it yet, but so I have 3/2 theta minus cosine of 2 theta minus sine of 4 theta over 4, and now I can evaluate. And you don't necessarily have to wait to multiply through by the 1/2 there. You could have waited till the end and got your, value inside and done it that way if you prefer. But okay, are you ready to substitute these values in? They're ugly ones, man. All right, so I have 3/2 times 7 pi over 2 minus the minus the cosine of 7 pi over 6, since it's double angle, minus 1/4 sine of, so I would have 7 pi over 3. And we have all of that minus 3/2 times negative pi over 12 minus the cosine of negative pi over 6 minus 1/4 sine of negative, where was I? Negative pi over 3. So either with your calculator or some unit circle remembrances, we're going to evaluate most of these, right? In fact, all of them happen to be unit circle values, so that's good. The first piece over here would be 21 pi over 24. And there's another one of these over here, right here, which would be plus 3 pi over 24. Oh, look at that. What does that equal? It does equal just pi. I'll get to that in a minute, but it will. Cosine of 7 pi over 6. Y'all are going to have to help me. What do you got? That's what I have written down. What do you? Okay, and then you've got a negative in front of it, so it'll be positive, right? So I've got positive, and you said square root of 3 over 2. Okay. Minus, and I have a 1/4, and then I need the sine value at 7 pi over 3. Square root of 3 over 2. All right, I already distributed the negative and the through to the first piece and moved it, but the second piece is now a positive. Cosine of negative pi over 6. Square root of 3 over 2. So I have square root of 3 over 2 for that one. And then I have another positive minus a negative of 1/4. And then I needed the sine value of negative pi over 3. Okay, everybody good? It's a lot of simplifying. I hope we did it all right. All right, so here's a pi at the beginning. I have square root 3 over 2 and another square root 3 over 2, and I have another 1/4 square root 3 over 2. How many square root 3s over 2s do I have?
Well, we got plus root 3 for one.
That's true. This piece and this piece would be plus square root 3. Let's just go ahead and take care of that. And then I have minus the square root of 3 over 8. And I have,
Could we do minus root 3 plus 1 over 8?
we're going to have to combine everything that's got the non-pi parts together anyway in the end. So let me just write it down for now. I have minus, what else is here?
1 over 8.
I don't think it is.
What is it?
Negative pi over 3 is not negative 1/2. I think it's negative root 3 over 2.
Okay, I was thinking that I don't have this answer in my notes, but that doesn't always mean that my notes are right. This one?
Yeah.
It is negative though, isn't it? Okay, well, that's good. It'll simplify more.
That means it's root 3 over 4. You combine both of them.
Those two pieces together, yeah. So this is root 3 over 8 again, so I have root 3 over 4. So this is negative 1/8, negative 1/8, and positive 1. What does that give me? I think it's 3/4. 3/4 square root of 3.
I have that except wait.
Wait, never mind.
I have negative pi and then plus 1. So I don't know what I did.
Yeah, there's a 1 right here, so this is positive 1, and then I have 1/8 and 1/8 from the denominators here that are negatives. So I should have positive 3/4 when I'm done of square root of 3s.
Right.
All right, basic idea, the trig and so forth in it is messy, but we got the idea, right? Even if you needed a unit circle or your calculator to finish out the details, we could do it, yes? Yeah, we could do it. All right, this title of the section was about area and arc length, and we've done the area, so now we're going to do the arc length. So let's take a look. Theorem 1014. This is arc length and polar. Let f be a function whose derivative is continuous on the interval from alpha to beta. The length of the graph of r equals f of theta from theta equals alpha to theta equals beta is s equals the integral from alpha to beta of the square root of the derivative of f squared plus f of theta squared. Or if you prefer to write it in terms of the r's that we had, specifically, you can think of it as being written as r squared plus dr d theta squared d theta. I wish I could go through this with you. I have it in my notes. I just don't think we have time to deal with it today, where this formula comes from. So it's actually coming from the derivatives of the x and the y individually in terms of the thetas, and then completing them and simplifying them down, and it becomes this underneath our radical. So there are pieces that are missing from what I'd like to show you, but we're short on time. So. Are you okay, Shayna?
Is that a large S or a
Small. Arc length is always done in terms of the small s, and then when we do our area formulas, they're often in terms of a larger s. They're using a small s. We did. Yeah, we've been working on area. Right now we're going to work on arc length. Yes. Okay, am I good to switch to slide? Yeah? Okay. All right, so our example, we're going to find the arc length of the given curve. And our equation that we're dealing with is r equals 2 plus 3 sine of 3 theta. All right, so the formula over here, I'll just flip back real quick, hinged on knowing r, which we know, and r prime, right? The derivative of r, or dr d theta. So the first thing we're going to find is dr d theta, or r prime if you prefer. So what is the derivative of 2 plus 3 sine 3 theta?
9 cosine 3 theta.
Yep, 9 cosine of 3 theta. And that's coming from the chain rule, that 3 on the inside being multiplied by the 3 on the outside when we're all said and done. That's what we have to find. So we need to graph our original function and see what our alpha and our beta go from and to.
I think it's 0 to 2 pi.
Yeah, I think it is as well. That's what I have in my notes, but I don't have any justification for that. So we'll double check to make sure that I didn't write it down or that everybody sees the same thing. So do 2 plus 3 sine of 3 theta. And kind of our default when we don't know what to do is always going to be 0 to 2 pi. And mine looks like ooh, it's all crooked and everything, but there it is. So kind of looks like there's 3 petals, but if you were watching it when it graphed, or if you look real carefully on the inside, there's some other petals inside as well, some smaller ones. Did you ever see that graphing when yours calculated it? Excellent. So the length of our curve would be how long it takes for it before it starts repeating itself. If you weren't sure this was all of it, of course you could increase the theta value a little bit further to see. Okay, is everybody good with that? So our alpha and our beta are going to go from 0 to 2 pi. And we have the square root of the original function, 2 plus 3 sine of 3 theta squared, plus the derivative that we just found, 9 cosine of 3 theta squared d theta. And we're going to clean up as much as we can, all right? So let's see what happens. All right, so when I do the squaring over here, I have 4 plus 612 sine of 3 theta plus the sine squared of 3 theta. I almost wrote sine cubed. And then plus 9, so I've got 18 cosine of 3 theta. Cosine 81 is what I meant to write down, really and truly. Absolutely. 81. And there's my squared. Thanks. I just transposed it. It's okay. Mhm. Yep, I left that out too. Moved past that pretty quick. Thanks. Okay, so potentially you might be interested in seeing if there's anything we can do with the sine squared and the cosine squared, because sine squared plus cosine squared equals 1. Unfortunately, they don't have the same coefficient, so I can clean it up some, but it's not going to be perfect. The other thing is that if we're hoping that this might simplify with algebra later, having sine and cosine underneath the square root is not especially helpful. Having only one or the other would be better. So since I've already got a sine 3 theta here, I'm going to change my cosine squareds into sines. Does that make sense? Okay. So the first part stays the same. And then, if you'll remember, when we do these kinds of substitutions, cosine squared would be 1 minus sine squared of the same angle, 3 theta, that we had before. So the simplification at the end will allow us to combine a little bit of what's going on. Okay, let's see, I've got a 4 and I've got a negative, I'm sorry, yeah, positive 81. The negative's next. That's 85. Plus 12 sine of 3 theta. And then we have sine squareds. How many sine squareds do we have? Ooh, 72. Negative 72. Yes. Okay. So, at this point, there's no way that that inside is going to be able to factor into a perfect square trinomial, correct? You guys with me? Sometimes they do. We encountered one last time, I think it was, where we had something factor into a perfect square trinomial. When it gets to the point where it won't factor into a perfect square trinomial, any guess as to what you're going to do to finish the problem?
Plug it in.
You're going to use your calculator to plug it in and approximate. We can't square root, I'm not sure what you were thinking, Shana, but there's no square root simplification we can do. Because I would have to have a perfect square underneath to simplify with the square root on the outside, and there's just not a perfect square on this one. Yes?
And, this was a little bit earlier, but how are we sure that 2 pi doesn't repeat any of it again?
We didn't look at it, but if you use your calculator, you'll see. I mean, like if you just estimate it again, so like make it go to 4 pi, and you'll see that that the calculator will continue to scroll, but you won't see any new information being added to your list of into your graph. Yeah.
Okay, but we probably could have done that algebraically as well.
Yeah, we could have. We could have.
Okay.
Did you get an approximation?
59.09.
Mine's not that.
How do we plug it in?
Just into the calculator. Maybe you guys haven't seen that before, so let me do that just in case.
Math 9.
Not everybody learns that in their Calc 2 classes, but you're going to put into your equation. All right, so you're going to have to manipulate. We're changing what we have in here already. So we'll have the square root of 85 plus 12 sine of 3 theta minus 72, and then I need sine of 3 theta squared, like that. So you make sure you do some double parenthesis stuff going on, depending on what mode you're in. Okay, did it look like that? 41's what I have, approximate. Yeah,
That is not what
that's not what you did.
I did the integral function on the calculator.
You can do the integral function, but you need the integral of this. Like this is still what we're taking the integral of.
Yeah.
Did you do the integral of the original equation we had in a minute ago of our?
No, I took the integral of that.
You just plug it in.
Why would the original?
Because we're not finding the integral of the function that's r. We're finding the integral of the stuff that's first.
So
Yeah, I'm just not there yet. I haven't finished it.
Oh.
Yeah, I'm gonna get there.
I got the wrong answer.
Okay, well, there might be a typo in what you looked at.
Big time.
So I'm just putting it in here because for me, it makes more sense when you did math 9, right? My math 9 looks like this. Actually, I'll use yours in a minute here to show you what it is. So in my math 9, I have to tell it that I'm putting in a function in first. So if I've already got it in y1, I can just take y1 here. And you could do the same thing too. So if you put all of the long drawn out function in y1, then in this screen, you could just tell it y1. And then I have to tell it x, in this case theta, lower limit 0 and upper limit's 2 pi.
How did you do the one?
Vars, oh my goodness, that's not what it was supposed to be.
That's correct.
I got
Huh?
41.5.
That's what it's supposed to be, so I have a typo as well.
I plugged it into the integral thing.
The,
Yeah, I have 41. I have an
Oh.
integral.
Huh?
that one?
Yeah.
Yeah. No, but I do too.
Maybe it's thinking that I'm squaring the theta out.
You have to make sure that d theta, you put that in at the end too, because
Yeah.
mine came up with an error when I did. I forgot that.
Got that.
How do I find the
Let me
Y1?
see it.
It's not that hard.
It's underneath vars.
That is now 5.
VARS, there's a button that says vars. Right here, do you see mine? Vars, Y vars.
Are you in?
What did I do wrong? The answer is supposed to be 41.54.
I got 98.
Okay.
I just got 498.
Okay, let me see what you have, Hannah. Yours is showing up right.
Sorry, it's loading.
Yeah. What? Why?
Because you're squaring
She put Y1.
Yeah, you have to put the
Zero
sign.
to 5. I don't know what the order is.
What did he say he didn't do?
Y1 theta.
I didn't put my sign.
Yeah, mine did too.
Square root of 85 plus 12 sine 3 theta minus 72 sine of 3 theta
You can break it by hitting on. You can hit second on and break it.
squared. Oh, is that somebody's phone?
Are you squaring?
Wow, this is normal. This has become.
Okay, this is not supposed to have a problem. I'm not sure what I'm doing wrong on my calculator. Obviously, I did it right earlier because I have the 4154, which is right. Well, I don't see.
You need another parenthesis.
Yeah, because you.
Nope.
So the 72 won't be.
Yeah, I'm just thinking that was, okay.
I am not sure what I'm typing in wrong because it's not.
Yeah, what you had previously proved it. Right.
I got 4 different answers now. My calculator says I broke it.
Your calculator says you broke it. That's
It says
awesome.
error break.
Okay, we're gonna stop. We're gonna stop right here. All right, it's supposed to be 41.54.
Still put this on the test?
I'll figure out what's going on with the calculator. This is not a calculus problem. This is a calculator problem. So we'll figure it out. All right, aside from the weird calculator problem stuff, let me give you the assignment.
This is 10.
This is page 731. This is 10.5. Number 6, 9, 12, 15, 51, 54, and 56.
This is 10.5.
10.5, yeah. No, because I'm not going to finish 10.6. I can write a little bit of it down. It's not very long. The whole lesson itself is very short, but we won't finish it in the next 8 minutes. So,
I guess we're done.
no, we're going to use the next 8 minutes to start.
I didn't realize there was a 10.6.
There is a 10.6. All right, everybody has this? All right.